everyone, in this video I'll be talking about polymer chemistry. This is the first video about the playlist of polymer chemistry, and I'll be talking these things from the book called Organic Chemistry written by Janice Smith. And my name is Fayaz. I'm doing PhD from UNSW Sydney, Australia in chemistry. So let's start this video. And for this video I'll be talking again once I'm mentioning the Organic Chemistry book written by Janice Smith. If you guys need this book, then please drop your email in the comment section. I'll send you the book by email. Now in this chapter we will be discussing the introduction of polymers, and then we will be discussing topic of chain growth and polymers, addition polymers, anionic polymerization of epoxides, Ziegler-Natta catalyst and polymer stereochemistry, natural and synthetic rubbers, step growth polymers, condensation polymers, polymer structure and properties, and we will be discussing green polymer synthesis, and then we will be discussing polymer recycling. Now if you allow me to this one, maybe a little bit zoom it. Okay, how am I gonna zoom option, and no full screen. Okay, we are fine with this. Just increase the resolution. Yep. So everything that you see almost in commercial products is made up of polymers, like these plastic PPEs, bottles of cold soft drinks. They are all made up of this polymer, like polyethylene terephthalate, PET. We call it PET. So that is a polymer that is responsible for these making of these bottles. PET, it's an abbreviation of polyethylene terephthalate, is a synthetic polymer formed by the reaction of ethylene glycol. It's an material organic compound that is the diol functionality. I'm highlighting it. It's contain two OH groups and two CH2 units and a terephthalic acid. So when terephthalic acid reacts with ethylene glycol, then polyethylene terephthalate polymer is formed, which is responsible for the making of these soft drink bottles. Because PET is a lightweight and impervious to air and moisture, it is commonly used for transparent soft drink containers. PET is also used to produce synthetic fibers, sold under the trade name of Dacron. Of the 6 most common synthetic polymers, PET is most easily recycled, in part because beverage bottles that bear the recycling code 1 are composed almost entirely of PET. Recycled polyethylene terephthalate is used for fleece clothing and carpeting. In chapter 30, which is this one, we learn about the preparation and properties of synthetic polymers like polyethylene terephthalate. So in this chapter we're discussing polymers. What are polymers? Polymers are large organic molecules composed of repeating units called monomers. This is how we define polymers. So word poly means many and mer means molecules, and these are the large organic molecules composed of repeating units that we call them monomers, and mono means one and mer means molecule, that are covalently bonded together. So I'm highlighting this. This is the definition of a polymer. This is how we define polymers, that these are the large organic molecules composed of repeating units called monomers that are covalently bonded together. Polymers occur naturally as in the polysaccharides and proteins. Proteins and polysaccharides, these are called biopolymers. Or they are synthesized in the laboratory. So polymers can be found naturally as well as polymers can be synthesized in the laboratory. But this chapter concentrates on synthetic polymers and expands on the material already presented in chapter 15 and 22. And this book is Organic Chemistry, written by Janice Smith. Thousands of synthetic polymers have now been prepared. While some exhibit properties that mimic naturally occurring compounds, many others have unique properties. Although all polymers are large molecules, the size and branching, these two are important things in polymer chemistry. Size and branching of the polymer chain and identity of the functional groups all contribute to determining an individual polymer's properties, thus making it suited for a particular product. So a polymer is a large organic molecule composed of repeating units called monomers that are covalently bonded together. The word polymer is derived from Greek word poly plus meros, meaning many parts. Polymerization is the joining together of monomers to make polymers. The process by which polymers are made is called polymerization. Synthetic polymers are perhaps more vital to the fabric of modern society than any other group of compounds prepared in the laboratory. Nylon backpacks and polyesters, clothing, car bumpers and CD cases, milk jugs and grocery bags, artificial heart valves and condoms, all are these products, and innumerable others are made up of synthetic polymers. Since 1976, the US production of synthetic polymers has exceeded its steel production. Figure 30.1 illustrates several consumer products and the polymers from which they are made. Synthetic polymers can be classified as chain growth or step growth polymers. Chain growth polymers, also called addition polymers, are prepared by chain reactions. That's why they are called chain growth polymers. These compounds are formed by adding monomers to the growing end of a polymer chain. The conversion of vinyl chloride to polyvinyl chloride is an example of chain growth polymerization. These reactions were introduced in this section of this book. So this is the vinyl chloride. It's a monomer. If we react this vinyl chloride in the presence of any initiator, then we can prepare polyvinyl chloride. So you can see the monomers like vinyl chloride, they join together to make a polymer. So the figure 30.1 shows that which polymers are commercially used. Polymers in some common consumer products like Lexane is a name of polymer. Here is the structure of that polymer, and that name of that is polycarbonate helmet and goggles. So you can see these ones. And nylon 66 backpack. So these are made up of this compound, and this polyethylene water bottle is made up of this compound, and the rubber of these tires is made up of this molecule. So all of the stuff that a bicycle rider uses is made up of polymers. It's a wondrous world, and the polymers make a lot of materials that we use in our daily life. As is mentioned in the book, we are surrounded by synthetic polymers in our daily lives. This cyclist rides on synthetic rubber tires, drinks from a polyethylene water bottle, wears a protective Lexan helmet and goggles, and uses a lightweight nylon backpack. So these are all things that this bicyclist uses are made up of polymers. Step growth polymers, also called condensation polymers, are formed when monomers containing two functional groups come together and lose a small molecule such as water or HCl. For example, this diamine and this diacid chloride, these are the two monomers. If they join together, a polymer reaction can take place and it can give you the nylon 6,6 polymer. In contrast to many of the organic molecules encountered in chapter 1 to 26, which have molecular weight much less than 1000 grams per molecule, polymers generally have high molecular weights ranging from 10,000 to 10 power 6 grams per mole. The big difference between polymers and other molecules is the molecular weight. So polymers possess huge, massive molecular weight compared to small molecules. Synthetic polymers are really mixtures of individual polymer chains of varying lengths, so the reported molecular weight is an average value based on the average size of the polymer chain. By convention, we often simplify the structure of a polymer by placing brackets around the repeating unit that forms the chain, as shown in figure 30.2. This is a problem for you guys. Give the shorthand structures of polyvinyl chloride and nylon 6,6. If you can't solve this problem, please tell me in the comment section below. I'll try to give you the answer. Now let's discuss the chain growth polymers or addition polymers. So chain growth polymerization is a chain reaction that converts an organic starting material, usually an alkene, to a polymer via a reactive intermediate, a radical, cation or anion. So chain growth polymerization starts with an alkene in the presence of any initiator and it gives you the polymeric compound. The alkene can be ethylene or a derivative of ethylene. The substituent Z in part determines whether radicals, cations or anions are formed as intermediate. So what sort of intermediate will be formed depends upon which sort of substituent is attached, and that is the Z. An initiator, a radical, cation or anion is needed to begin polymerization. Since chain growth polymerization is a chain reaction, the mechanism involves initiation, propagation and termination. So these are the three stages that are involved in the mechanism of chain growth polymerization. And which sort of intermediate it involves, it may be radical, cation or anion. And what is the starting material for chain growth polymerization? It is alkene. If you see an example of chain growth, drawing a polymer in a shorthand bracket representation. So this is the large bracket and we put N. This is called a repeating unit and this is the monomer. Again, this is the terephthalic acid and this is the ethylene glycol. These two are monomers. When they react to give you the polyethylene terephthalate, and we put large brackets and small n and we call it as a repeating unit that will be repeated so many times in the chain. In most chain polymerizations, an initiator adds to the carbon-carbon double bond of one monomer to form a reactive intermediate, which then reacts with another molecule of monomer to build the chain. Polymerization of CH2 double bond CHZ results in a carbon chain having the Z substituents on every other carbon atom. What polymer is formed by chain growth polymerization of each monomer? So this is a problem for you guys to solve. So if this is the monomer A, B, C or D, as you know that these are the monomers that we can be used in the chain growth. So you have to write the product. So what polymer is formed by chain growth polymerization of each monomer? Think about it. If you want to write down the answer, then take a picture of the answer and put your answer in the comment section. I'll check your answer and get back to you. Have a look at the radical polymerization. Radical polymerization of alkenes was first discussed in this section and is included here to emphasize its relationship to other methods of chain growth polymerization. The initiator is often a peroxy radical, which is this one, formed by cleavage of the weak oxygen-oxygen bond in an organic peroxide or double bond or double oxygen or. Mechanism is this one. So the first step is initiation, which we call formation of a carbon radical in two steps. So the bond between oxygen and oxygen breaks down and two radicals are formed, and the radical oxide reacts with the alkene double bond, and through homolysis of the weak oxygen-oxygen bond of the peroxide forms RO radical, which then adds to a molecule of monomer to form a carbon radical. Part 2 is propagation. Growth of the polymer chain by CC bond formation. So this is the free radical, and that reacts with this double bond, and they join together to give you this new CC bond radical. In step 3, the carbon radical formed during initiation adds to another partner, another alkene molecule, to form a new CC bond and another carbon radical. Addition gives the more substituted carbon radical, that is, the unpaired electron is always located on the carbon atom having the phenyl substituent. Step 3 occurs repeatedly, thus growing the polymer chain. Part 3, termination. Removal of radicals by formation of a sigma bond. So part 3, our third step in the mechanism, is termination. So in this step it happens removal of radicals by formation of a sigma bond. So two radicals combine to give you this sigma bond. To terminate the chain, two radicals can combine to form a stable bond, thus ending the polymerization process. So this is the mechanism. These are the steps that are involved in radical polymerization, and it starts with the formation of a radical, and then that radical adds across the double bond of alkenes. Radical polymerization of alkenes is favored by Z substituent that stabilizes a radical by electron delocalization. Each addition step occurs to put the intermediate radical on carbon bearing the Z substituent. Where styrene is the starting material, the intermediate radical is benzylic and highly resonance stabilized. So figure 30.3 shows several monomers used in radical polymerization. So ethylene, vinyl chloride, styrene, vinyl acetate. These are the monomers which are used in the radical polymerization reactions. How we can say the benzylic radical cation or radical formed from the styrene is resonance stabilized? You can see from these resonance arrows that they are involved inside the delocalization of this pi electronic cloud present in the benzene ring. So 1, 2, 3, 4, 5. These are the 5 contributing structures, or the 5 resonance structures for the benzylic radical can be suggested or can be formed. And now for you guys to do some exercise. So problem 3, 30.3. What polymer is formed by the radical polymerization of each monomer? So if you have this monomer, then what polymer is formed by radical polymerization of each monomer? If you have this monomer, what will be the polymer that will be formed from this? Like for example, styrene was the monomer, this is styrene, and this is the polymer that is formed from the styrene. So follow the same mechanism, just replace this styrene with these monomers. You can use these ones as well, 4, or you can use these questions given in this problem. Problem number 30.4. Draw the mechanism for the radical polymerization of vinyl acetate using this as an initiator. Here the initiator was general R double bond oxygen, but here in the question it's given to you which kind of initiator you will have to use. So these are the two oxygens, so the bond between this oxygen and oxygen will break. You don't need to worry about these alkyl groups. So try to attempt the answer of this question, but if you can't answer the question, then please drop down in the comment section. I'll tell you the answer. But I would suggest you, I will recommend you to first attempt the answer yourself. But if you cannot answer it, or if your answer is incorrect slightly, then put the picture of the answer in the comment section, then I'll check your answer and then get back to you. Chain termination can occur by radical coupling as shown in mechanism 30.1. This is called radical coupling. Chain termination can also occur by disproportionation, a process in which a hydrogen atom is transferred from one polymer radical to another, forming a new CH bond, one on one polymer chain and a double bond on the other. So these are the radicals. Disproportion, one method of chain termination. This is the new CH bond formed, and this is the new pi bond is formed. This is called disproportionation, and this is involved in chain termination. Either termination could occur through disproportionation or through radical coupling such as this. I think I should stop here now, and we will continue from this chain branching in the next video lecture. But if you have any questions regarding this video, then feel free to ask me in the comment section, or if you need this book of organic chemistry written by Janice Smith, then I'll email you the book. Drop down your email below in the video. And once again, thanks for watching. Take care. Bye.